to my screen. Full screen. Now, is my screen is visible?
Yes, it's visible.
Okay. Today, I am going to present my recent published work with Professor Nabamita Banerjee. That is logarithmic correction to the entropy of non-extremal black holes. Okay, how to remove this? Okay, logarithmic correction to the non-extremal black hole entropy in n=1 Einstein-Maxwell supergravity theory. The basic outline of the whole talk will be as follows. First, I will present the basic introduction about the research work. Then, I will present the hit kernel methodology used in the research work. And we will have a general introductory about non-minimal n=1 Einstein-Maxwell supergravity theory. And then we will apply hit kernel technique to this non-minimal n=1 Einstein-Maxwell supergravity theory and compute some fundamental hit kernel coefficient, Srikant coefficient, and a particular Srikant coefficient will be used to determine logarithmic correction of non-extremal Carnot-Neumann family of black hole in non-minimal n=1 Einstein-Maxwell supergravity theory. So let's begin the talk. So from the works of Beckstein and Hawking, we have proposed that black holes are thermodynamical objects which possess a definite entropy, classical entropy given by area of this relation. But this entropy relation has a limitation which does not depend upon the matter field present in the black hole background. It is limited to two derivative terms. So considering the quantum fluctuation, the matter field and higher derivative term, this entropy, classical entropy, demands correction. And so a full quantum corrected entropy relation can be given as follows, where we are particularly focused in this logarithmic correction factor, and most importantly this C factor, which encodes the matter field and the interaction in the background, which will be given by the host supergravity theory. And the rest of the terms will encode the high derivative correction and massive correction, etc. So logarithmic correction, these are leading order quantum correction which arises from massless field and their coupling with a black hole background at one loop level, and these corrections act as an infrared window into the microstates of black hole. A successful comparison of logarithmic correction between microscopic and macroscopic, one can test a consistent theory of quantum gravity. Although our work is limited only the logarithmic determination of supergravity theory in the macroscopic part. Okay, the whole plan of the whole talk is as follows. The objective is to determine the logarithmic correction to the entropy of non-extremal Carnot-Neumann, Kerr, Disney-Nostrom, and Schwarzschild black hole in n=1 Einstein-Maxwell supergravity theory. And for this, we will use hit kernel expansion technique proposed by Vasilevich for this purpose. And we will determine firstly hit kernel coefficient, that is Srikant coefficient. And then we will utilize the third coefficient for determination of logarithmic correction of non-extremal black holes. So first we will have a basic review about, we will review the hit kernel methodology presented by Vasilevich. Hit kernel expansion is considered as effective way to analyze the effective action of a theory. So W, which is a one loop effective action, is related to the connected differential operator lambda of a quadratic fluctuated action in this way. In order to study the spectrum of the differential operator, we impose the hit kernel K, which is a solution of fundamental equation which can be expressed as this exponential of connected differential operator. And here, in order to counter the divergence in the lower limit regime, we impose the UV limit epsilon, which is tuned with Planck length LP. So with this boundary condition, this hit kernel K permits a perturbative expansion in small s in this way. In this where A0, A2, and A4 are hit kernel coefficient. Although our work is particularly fixed on this S-independent part A4, which we will later used in this integration part, and we will determine the logarithmic divergence via this hit kernel coefficient A4. Okay, now we will present the methodology how to compute this Srikant coefficient A0, A2, and A4. So beginning with the qualitative fluctuated action, which can be expressed as this way, where this kinetic differential operator lambda is something like this form, where positive is sign is for boson and negative sign is for the fermion. The lambda should be Laplacian and Hermitian as per the prescription of Vasiljevic. And this form of kinetic differential operator is to be made it to fit in this prescription of lambda, where G is the effective metric and N is the matrix related to the derivative part, and P is the matrix related to the non-derivative part associated with this kinetic differential operator. And now here there is a new effective covariant derivative is imposed, which is related to the ordinary covariant derivative along with via field connection omega, which is relating the different fields of different spin indices. Now, comparing these two kinetic differential operators, one can evaluate the respective expressions of E omega I by the in terms of N and P. And a generalized field strength omega can also be defined in this way, which is associated with the curvature of the background metric and as well as the connection field omega. So after computing all these intermediate ingredients, one can determine all the first three Srikant coefficient, that is A0, A2, and A4 by respective computing the traces of their respective intermediate ingredients, which is computed here. So in the above expression, we have, as we are particularly focused in Einstein-Maxwell system, so we have considered, we have put R is equals to 0 in the above relation as such a system satisfy the Ricci flat space, and also ignore the total derivative which integrate to 0. So now we will start a basic non-minimal n equal to 1 Einstein-Maxwell supergravity theory, as we are particularly interested in Kahneman family of black hole, which are solution of Einstein-Maxwell theory. In concept of n equal to 1 supergravity theory, ever black hole configuration can be expressed as coupling pure n equal to 1 supergravity with a vector multiplet, and supersymmetric action of such a theory is well studied by Faraday. And it is a tabular format of showing the field content of respective bosonic and fermionic sector of a supergravity multiplet and vector multiplet of n equal to 1 supergravity theory. So in this theory, the one vector multiplet is non-minimally coupled to supergravity theory. And the action is supersymmetric action is well studied in the paper of Faraday. We have extracted the only one loop part of the action of this from one loop part of the action from this paper, although there is a four fermion interaction term is also there in their work of Faraday, but the one loop interaction from the four fermion interaction will vanish because of vanishing of background field in the Einstein-Maxwell system. So here one can see that the gravitational field is non-minimally coupled to Gaussian field. So we nomenclature this theory as non-minimal n equal to 1 Einstein-Maxwell supergravity theory, and rest of the notation have usual meanings. So arbitrary solution G mu satisfying the ordinary Einstein-Maxwell theory when embedded in n equal to 1 supersymmetric theory. Such a geometry satisfies Ricci flat space and the following equation of motion and the Bianchi identity and the Maxwell equation. And these equations, these above equation will have a tremendous positive has effect in simplifying the Srikant coefficient in terms of local invariant, that is background gauge field, and in DC and demand terms. So now we will imply the heat kernel methodology to any non-minimal n equal to 1 Einstein-Maxwell supergravity theory. So imposing fluctuation in the metric and gauge field in the bosonic sector of action, that is L is equals to R minus F mu, one can get the gauge fixed quadratic fluctuated action of the bosonic sector, this one. Now imposing this field definition to this quadratic fluctuated action, this operation will ease the further computation of Srikant coefficient by shortening the expression of P omega and all the intermediate expression. This field definition approach of heat kernel is done in the words of Larsen, and we are motivated by their field definition approach of heat kernel, and we also impose this heat field definition to our theory as well. And in Larsen's paper, Larsen's work, they have computed the bosonic sector of n equal to 2 Einstein-Maxwell supergravity theory, which is same here in our case also, and reviewed their work and computed the Srikant coefficient of bosonic sector of non-minimal n equal to 1 axial mass of supergravity theory as follows. The bosonic result of this field-defined edge hit kernel approach obtained perfectly matched with the bosonic result of the general, that is without imposing any this type of field definition. From our earlier calculator, in our earlier work we have computed the same Srikant coefficient but without any such type of field redefinition. Although in that without using this field redefinition, the computation was very much large and tedious. So now again, beginning with the similar approach, we will start with the fermionic sector of fermionic sector action, which is represented in this way. Now again, implementing this type of field definition in this action, where by using this field definition, the kinetic part of this differential operator is a little bit simplified, which has great which simplifies the kinetic, which has great ease in the further computation of Srikant coefficients. Now this operator is linear in form. So first it has to be made Laplacian. So doing this operation, the form of lambda will be something like this. Now following the very same approach of heat kernel methodology, and the Srikant computation will be resulted as follows. So again, the result obtained from this again field defined heat kernel approach matches with the result of heat kernel as we have computed via general heat kernel in our earlier work, which checks the consistency of this heat kernel results. So adding the bosonic and fermionic sector along with the Srikant coefficient associated with the host part as well, the total Srikant coefficient associated with the non-minimal n equal to 1 axial mass of supergravity theory will be as follows, where we will now in the next we will particularly take this effort term and determine the logarithmic correction, which include logarithmic correction to the black hole entropy. So in order to determine the logarithmic correction of non-extremal black hole, we first reviewed the sense formalism to how to compute the logarithmic correction for the arbitrary non-extremal black hole. Then we imply this formalism, the formalism to our Coordinate metric, and so the entropy of the black hole, the log correction of non-extremal black hole can be represented as way where the effort is to be evaluated in the full geometry of the black hole background. And this there is a non-zero mode part and this is a zero mode part. This zero mode part is already been computed in various literature in the works of Sen and Ferrara, using all the results of the literature. Presented this schematic compact form of the zero mode term. So we used that schematic form for the zero mode computation and integrated our Srikant coefficient computed is into we use the Srikant coefficient here for calculating the local contribution to logarithmic correction. Here in the zero mode part, 3 is associated with the translation symmetry, and X is the rotational symmetry possessed by the black hole, and SU is the number of supercharges possessed by the black hole. Delta is 1 for non-extremal black hole and 0 for extremal black hole. So using this integration result around of one full geometry for the Riemann and Ricci coefficient tensor, where all the RH is the horizon radius and B is a scale which is related to angular momentum divided by mass of the black hole. The net logarithmic correction to the following non-extremal black hole for Kerr-Neumann, Kerr, Diesel-Nostrom, as certain black hole are as follows. Thank you.
Okay, thanks Gourav for finishing before time. Any questions? Hello.
Hi, Gourav. Have you heard of the name of the mathematicians Peter Gilkey, Kirsten, and Branson?
Gilkey, yes, sir. Yes, sir.
Peter Gilkey.
Okay,
So
okay,
I guess I know that there is this famous physics reports user manual of sorts by Vasilovich, but I think Peter Gilkey is basically I think the person that you may want to actually refer to when you talk about applications of the heat kernel technique.
Actually,
right?
yes, sir. This yes, you have said right. Actually, this Srikant coefficient result, this is A0, A2, and A4. Actually, these are first determined by Gilkey's paper. So yeah, Yes, that's it. Here I have should refer Gilkey.
Yeah, Sheshansu, can I just have one very small query?
Sure, sure.
I apologize, Gaurav, for displaying my ignorance, but I mean, what is so special about this n equals 1 Einstein Maxwell supergravity? Why do you guys?
Actually, sir, in the works of Ferrara, they have determined the logarithmic relation for n equal to 1 Einstein n equal to 1 supergravity theory, but those n equal to 1 supergravity theory belong to only consider only the minimal interaction part, not the non-minimal interaction part. So in order to motive to provide a because in the general action, which is of general action, there is a non-minimal coupling of non-minimal coupling to gravitational field and Gaussian field. So in order to provide a concrete result in the macroscopic part for the n equal to 1 theory, we have computed this result in non-minimal n equal to 1 Maxwell supergravity theory. And the works of Ferrara, they have considered only the minimal coupling, and it is due to their methodological limitations. So our result is concrete. That's why, and that's why you have computed. And again, in the microscopic sector, one can also test this result from our result to if one wants to determine the logarithm correction in the microscopic sector as well.
Okay, thanks, Gaurav. Can you unshare your screen? Aranya, are you there?
Stop share.
Yes.
Stop share.
Okay, can you share your screen?
Yeah. Good.